The one from yesterday is a good one too. We'll maybe finish that one up. Let's do this one first. This is an easier one.
Yeah.
Okay, so real quick, let's just review very briefly kind of how the calculus relates to these kinds of things that we're going to look for, these features on the function.
Thank you.
Okay, so relative extrema occur where?
There's peaks and valleys.
Okay, those are peaks and valleys. They occur at...
Where the derivative equals zero is undefined.
Okay, good. Critical numbers. First derivative critical numbers, which is where the derivative is equal to 0 or undefined, right? Okay, increasing, decreasing intervals, we get all that from the f prime row, yeah, from the test points, right? The first derivative test, okay? We started talking about some different stuff yesterday. We started talking about concavity, right? And we talked about how the second derivative is really just the rate of change of the first derivative, right? So think of it as the rate of change of the slope of a function, right? And we said a couple things before we jump into this. So a positive second derivative, we say is positive concavity or upward concavity, right? So what does that mean in terms of like a tangent line? Where does the tangent, we know that we have upward or positive concavity if the tangent line sits where relative to the graph? Below the graph, right? Below the graph. So if the graph is riding on top of the tangent line, that's an area of positive concavity. If it's riding below the tangent line, then that's negative or negative concavity, or we'd probably say downward concavity because it's bowl-shaped down, right? Okay? So like for example, if I just drew just a little function here, if I pick this point like right there, is that going to be positive or upward or downward concavity? Downward, which is negative concavity, right? Because the tangent line sits on top of the graph. How about right here?
Upward. Or no, downward.
Still downward, okay. How about right here?
Upward.
Upward, right there, upward. How about right about there?
Transition.
Inflection point, because if I draw the tangent line, look what happens. Half is above and half is, it's the point where it transitions from being, in this case, below to on top of the tangent line. Yes?
Why can't we just say that upward concavity is just
Well, because convexity, convex really just means, like in physics, convex would mean bowed outwards. But there's really no up or down with that. I mean, it just, see what I'm saying? Like you'd have like a convex lens would be a lens that a profile did that. You could hold it this way or you could hold it this way. Concave lens would be one that's this shaped. Right? Okay. So this is our, what do we call that place right there? That's an interesting place. Yeah, good. That's, I'm running out of virtual ink again. That's an inflection point, right? Inflection point would be a transition of concavity. So it's a transition of the sign of the second derivative, right? Okay, so think of the second derivative in the same, parallel to the first derivative, sort of, right? We do the same kind of stuff. If we're looking for inflection points, that would be like looking for relative extrema with the first derivative. So, what do we do? Well, we find critical numbers for the first derivative and then just test them, right? Same thing for the second derivative. We're going to find second derivative critical numbers and then just test them to see if they are inflection points. Okay? That make sense?
Yeah.
Okay, so now let's kind of, we haven't put all this together yet though, so let's put all this together in a problem. All right, so first step,
Find the derivative.
take the derivative. What do I get?
6 squared. Minus 6x minus 12.
Okay, and while we're at it, because it's a polynomial, we'll just crank out the second derivative also, right?
Sure. You can make it easier if you simplify it. Okay.
Well, okay, but we don't want to
Oh,
you don't want to simplify it until after you
Yeah.
start to do something with it, right?
Yeah.
Otherwise, it affects the second derivative. It makes it incorrect. So what do we get for our second derivative?
12x minus 6.
Okay, so now we can find our critical numbers. And these are gonna be easy to find. These are all polynomials, right? So we don't have to look for any weird places where the derivative is undefined. Polynomials are defined everywhere. What's gonna be the equation that when I wanna solve for the zeros, I could simplify it, right? 'Cause I'm just trying to find the places where it's zero. I could factor out, a 6?
Yep.
So I'm gonna say this is equal to,
Wait, don't we just solve for x?
yeah, we do. We're gonna set it equal to 0 and solve for x. Let's go ahead and factor it. So if we factor out a 6, then we're left with x squared minus x minus 2. What's that gonna factor into?
X minus 2, x plus 2.
Good, and then that's all equal to 0, right? Okay, bottom one, we could just factor out a 6, I guess, on the bottom one. So where does this equal 0? The first derivative?
0.
2 and negative 1. Okay, so our first derivative critical numbers. So first, what are you gonna call that? How are we gonna label that? I can't remember how you used to do that.
dy.
Critical number, we'll just do first. First derivative critical numbers are x, you already told me x equals 2 or negative 1. How about our second derivative critical numbers? 1/2. Okay, and we can make our table, right? Okay, so there's our x-axis.
Isn't it x equals 2? Yeah, x equals positive 2 and negative 1 for the first derivative.
Positive
Yeah.
2.
Yeah, it is.
That's an equal sign. Okay.
Yeah, there you go.
Sorry.
Sorry. Do you not include 0 on the?
Why 0?
Oh, you did factor out x. Never mind.
Yeah. Yeah, does that make sense?
Yeah.
Okay. Okay, I'm going to show you another cool trick here. We haven't actually learned the second derivative test yet. We talked about the meaning of the second derivative, but let's put all the important stuff up here. Well, first of all, the domain is unrestricted. So we could indicate that by including the entire real line. And now we're going to put up critical numbers. Okay, so first derivative critical numbers. We had negative 1 and positive 2. Second derivative critical number was 1/2, right?
So it still goes up top too?
Yeah, so it goes up top. Now we can remind ourselves which is which by putting zeros there and there, right? Okay, so let's just use the first derivative test here for a second. We're about to discard that. And the first derivative test is still going to be useful to us in certain instances, but whenever we can, we're going to end up using what you're about to learn, which is the second derivative test. But for now, let's go back to the first derivative test. So what do we need to do for our first derivative here? Test points. So what would you suggest for test points?
0.
0 would be, sure, why not 0? Oops, so wrong place. So 0 would go like right there.
Yeah.
Okay.
Negative 2.
-2, sounds good. And 1, actually, we don't even, for the first derivative, we don't even need to worry about that one, do we? You see what I'm saying? Because this is
yeah,
that's a
that's
second
part of the
derivative
second.
critical number. So we could jump clear over here to like 10 or something. Just some number. Sometimes I like to use numbers that are like more extreme, so it's easier to evaluate the signs.
Just something between 2 and -1.
So we picked 0. Now we could have actually picked 1/2, couldn't we? Right? I mean, but maybe we don't want to because it's a fraction. 0 is pretty easy to evaluate. 0 is generally a pretty good choice. So if we now are evaluating the sign of the first derivative at -2, what's going to happen? At -2, this is always positive, right? At -2, this is negative, and this is negative. So the overall sign is
Wait.
positive. Positive times negative is positive, right? So here we get positive at 0. we'd get,
I thought we were using
at 0, we'd get positive times negative times positive is
negative.
negative. And then at 10, we'd get everything positive, wouldn't we? Okay, so what's that tell us then? What kind of a thing is that?
It's a downward concave.
Oh, interesting you said that. So it's going from increasing to decreasing. So it's a maximum, isn't it? Okay, so we know this guy is going to look like that. And this guy is going from negative to positive, right? So we know this one's going to look like that. But Delaney mentioned something there. A relative minimum would always have to be concave down, wouldn't it?
Yep.
Does that make sense? If it's a smooth relative minimum, at least, right? I'm sorry, maximum. You're right. I said it backwards. Maximum would be concave down. A minimum would be concave up, right? So, did we really need to check those test points, 2 test points around our critical number? Not really. Because look what we could have done. Look what we could have done instead. Instead, we could have said, okay, well, at x equals -1, which is our critical number, let's evaluate the sign of the second derivative. All we need is a sign. So if we evaluate the sign of f double prime at -1, what do we get? At -1, we're going to get 6 times a negative, right? Positive times negative. So we get a negative concavity. Well, now think what this means. If we have a horizontal tangent coupled with a negative concavity, what does that have to be?
I did not know.
It's got to be a minimum, right? Or maximum. Sorry.
Wait, why?
It's got to be a maximum because if I know I've got a horizontal tangent, right? I know that at that point the function is concave down. Think what concave down means. That means that the tangent line sits on top of the curve at that point. So it's got to look like that, right?
But didn't you figure that out using the number?
Okay, yeah, but now what I'm saying is that was a lot of work. We didn't need to do any of that stuff. We could go back and erase all that nonsense. We didn't even need it.
How does the negative show that it's concave?
Well, because remember the sign, that's what the second derivative tells us. First derivative, the function tells us value. It tells us the height of the function essentially, right? The derivative tells us the slope of the function. The second derivative tells us the concavity of the function. So wherever the second derivative is negative, that has to be a place where the function is concave down. Wherever the second derivative is positive, that's a place where the function is concave up, right? So if we know that at this critical number, the value of the second derivative is negative, then that guarantees it's concave down, right? So it has to be a relative maximum.
Then what about the 1/2?
Okay, well, we'll get to that. So now what about right here? Let's do the same thing over here. We don't even need these test points, right? If we've got the second derivative row in our function, right? So we can come down here and we can just evaluate the sign of the second derivative at x equals 2. Well, that's going to be positive, isn't it? Okay, well, now think what that means. If we've got a horizontal tangent plus a positive second derivative, that's concave up, which means the tangent line sits under the curve. Curve's on top of the tangent line. That's got to be a relative minimum. Okay? When you use the second derivative, there's a really easy way to remember this. When you go down to the f double prime, so if you're evaluating a first derivative critical number and you're looking at the second derivative row, if it's negative, well, that means the function's in a bad mood and it's frowning. It's very negative. But if the function is positive and upbeat, it's smiling. So it's happy, right? Okay. Now, we killed about 4 birds with 1 stone there because look what we also did. When we checked the value of the second derivative, the signs of the second derivative around this second derivative critical number, we found out that the second derivative is transitioning from negative concavity to positive concavity. So what is happening at this point? It's an inflection point. Yeah, it's an inflection point. And if we wanted to, we could even sketch what it has to look like. We know that it has to be one that's going from concave down to concave up, right? So we know it's that kind of an inflection point, right? So we could label all these things, and we know that this is a relative max. That's an inflection point, and that's a relative minimum. Okay? And if we want to get a good sketch of this curve, if we really want to get a good one, all we'd have to do is just fill in the second halves of these ordered pairs, and that's a pretty good sketch, right? So at x equals -1, what's the value of our function?
-2
Plus, yeah, -3, so -5, plus 12, so 7.
12, yeah.
At 2, we get 8, what is it? -20. I'll trust you. And at 1/2, oh, I don't want to do that. -13 halves.
Somebody might want to check. Because I did it. Oh, I don't know.
Well, let's see what we got. So we get 16 minus, oh, what am I saying? Not 16. We get 1/4 minus 3/4 is -1/2 minus 6. That's right. So it's -13 halves. Yeah, -6.5. Okay, so now look, we can make a sketch of this, can't we?
Yeah.
We know that this is going to look something like, the scale is going to be maybe a little bit off here. But we're going -1, 7, so that's going to be a point up here. We're at 1/2, so that's -1, so there's 1, 2. So at 1/2, -6.5, so that's going to put us like right down about there-ish, right? And then 2, -20 is like way down there. Scale's a little bit off, but you get the idea. So that tells us everything we need to know, doesn't it? Okay, so we know that the function locally is doing this. That's where it changes, right, to being concave up. How do we know about the endpoints, though? How do we know? Well, we would call these the tails of the function. So if we go really far out to the left or the right, that's pretty bad, but you get the idea. Now I gotta redo that. That's terrible. Right, so this one's gotta go. That's a little better. Well, how do we know what it does out here? Could it go like this instead? Could it go like that and be asymptotic?
Yeah,
Could it?
probably.
I say no.
Why?
No, there's a compelling reason that we know it can't do that. We know that it has to do the green thing. It can't do the red thing. Well, no, horizontal asymptote wouldn't be undefined. Those are okay. But we know it can't do that, for example.
It doesn't have any.
Okay. Want to say it again, Zoe? You'd need another inflection point, because look what would happen. You would go from being, let's look at the, see what I'm saying?
Yeah.
We would go from being concave down somewhere to being concave up. We'd have to pass through another inflection point, and there aren't any. How do we know that? Because there's only one critical number of the second derivative. So how many possible inflection points could there be?
One.
One, right? Okay, make sense?
Yeah.
Okay? All right, so do we want to, well,
What happens after the second derivative?
I'm just curious.
what happens after the second derivative?
Like, what are you
Oh,
measuring?
we don't even mess with it. Yeah, it's really hard to attach to a shape in it. Yeah. Okay, I think I'm gonna do a different one. Let's do. No naps.
Naps are good for you, remember?
No trivia. No, not today. Not today.
They have a 10-minute break.
Okay, let's do one like this. Oh. Okay, better do a trig one.
I hate this problem.
Were we gonna go back to that problem?
Yeah, let's do. Rather than have me, I'll do that one for tomorrow. I can write the whole thing out. So we'll start at the beginning or on Friday.
On Friday?
What's tomorrow?
Tomorrow, I'll let you work. Okay, so let's go through this. Are there any places where this function is undefined?
No.
So no asymptotes, right? Now, what is this telling us right here?
Only, we have a domain.
We have the
There's
Okay.
only one.
Okay, so Jolie, this is telling us this is a restricted domain, right? We're not going to let it go forever. It's a restricted domain. So if we wanted to, we could find like an absolute extremum here, but we're just going to find relative extrema and points of inflection and all of that stuff that we've been finding. Okay? So what's first step? Take the derivative. All right, if we take the derivative, let's see, the second derivative, or first derivative, sorry, is what?
2 cosine x
plus
plus cosine 2.
plus 2 cosine 2x.
What?
That's correct.
Yeah.
Because look, on this side, you got to take the derivative of sine hand is cosine hand times 2.
I need a
Why don't
page.
you times it by 2 at the end?
Well, you would, but
I just skipped, like, we did that.
yeah, so we really had a 2 back here, but we always want to put the constants in front of the function.
Oh, yeah.
Okay. So there's the first derivative. While we're at it, let's do a second derivative.
Negative
So we're going to get negative 2
sine
sine x.
minus 4 sine 2x, right? Maybe not sine
Yeah.
9.
That's right.
Yes.
I don't get it, but okay.
Okay, well let's talk about that. Okay,
Never mind.
do you see how we got it?
I get it.
Questions?
Just a skipping step.
Okay, so all we did here when we skipped the steps, the derivative of cosine of hand is minus sine of hand, right? And then the derivative of hand is 2. So we'll pull that other 2 out front, but 2 times 2 is 4. Okay? All right, so now we know that these are all defined everywhere, but we've got to find the zeros. So let's go back up to the first equation, and we want to set it equal to 0. So 2 sine x plus sine 2x. But what's the problem with that? If I set that equal to 0,
Wait, isn't it cosine?
I'm going, oh, actually, yeah, we don't need to do that one. We're not doing it.
Okay.
Can you figure out a 2? Maybe not? Maybe?
Yeah, we could.
Okay.
We could factor out a 2, that's fine. But we've got some other problem here.
They're different?
The x's don't.
Okay, yeah, the angles, right? The angles and the trig functions, or the arguments of the trig functions don't match up, and that's bad, right? We gotta have
Oh.
same kinds of angles, so we need a trig identity.
Cosine 2x can beat sine squared or something?
Okay, so yeah, you have your option. It's either cosine squared minus sine squared, or you could rewrite that. Remember that if we ever have, the only one you need to remember is this one. We know that cosine 2x is equal to cosine squared x minus sine squared x. But remember, we can always trade a cosine squared x for a 1 minus sine squared x, right? Because we've always got this identity to fall back on. Sine squared x plus cosine squared x equals 1. So if I want to rewrite this in terms of sines, I would solve for cosine squared x and get 1 minus sine squared x and substitute.
Yeah.
If I want to rewrite this in terms of cosines, I would solve for sine and substitute, right?
Yeah.
Well, which one do we want?
Sine.
We want,
Even.
well, the first term has a cosine in it, right? So we want to keep this in terms, we'd like to have a trig function in the same kind, a trig equation with the same kinds of trig functions,
Yeah.
right? So we're going to solve this where we're going to go ahead and let sine squared equal 1 minus cosine squared and subtract that quantity. So we get cosine squared x minus the quantity 1 minus cosine squared x, which gives me 2 cosine squared x minus 1. If I distribute the negative,
Yeah.
right? So that's, I mean, really, there's three forms to this. Either you could have it this way, or you could have 2 cosine squared x minus 1, or 1 minus 2 sine squared x. Those are all equivalent. Okay, but you don't have to remember the 2 bottom ones. You can always just derive them for yourself. Okay, so we're gonna write this as 2 times the quantity, 2 cosine squared x minus 1.
Ooh.
Where'd you get the 2 out front? And the 2 cosine?
Oh, wait.
But we
You're
took
taking
it
that out
out.
front. Is, remember?
Oh, yeah, never mind.
Okay.
You're right.
Okay.
You're right. Plus, okay. There you go. So then we can solve that.
How do we
So,
do that?
yeah, what can we do to that one? Well, we can rewrite this. This is really written in terms of cosine x, isn't it? So we've got now 2, oops. We've got 2 times the quantity, 2 cosine x squared, because that's what cosine squared x is, plus cosine x minus 1, right? That's just like saying this, isn't it? This is just like saying 2 times, instead of the cosine x, let's just trade that for z. So that's really like saying 2z squared plus z minus 1. Okay? What does that factor into? Well, I know if I've got a 2 there, if it factors, I've got to have a 2z and a z. Are there factors of -1 that make the cross terms work?
Equals 2z minus.
So it'd be plus
-2.
1 minus 1, right? And you just kind of trial and error. We know I'd give me 2z squared, I'd get a plus 2z minus a z is a plus z, and then a minus 1.
Yeah.
Okay, but we don't have z's. We have cosines, right?
Yeah. So
Right, so this is really equal to 2 times
Wait,
2 cosine x.
yeah. I think the plus and minuses are wrong on
Yeah, it's supposed to be minus
Minus-
z minus 1 and z plus.
Yeah.
Oh, yeah, you're right. You're right.
Imaginary numbers.
You're right.
I could be wrong.
So that should be minus. That should be plus. Yeah, that's right. Yep. Okay, you know what? I'm going to get rid of this thing just because it's getting in the way. We'll redo that one
Are we
later.
gonna do a trig analysis on the test?
Yeah, oh yeah. Yeah, you got to be prepared for some trig.
We're doing integrals after this test, right?
No, we got one more over derivatives and then we get into integrals.
Oh, really?
we're almost done.
I talked to a lot of people about derivatives, or about integrals, and they didn't like it.
Integrals?
Yeah.
Oh, integrals is good stuff.
Do we forget about derivatives?
No.
Okay, is everybody okay with that? Okay, focus please.
Can you like show us the steps on how to do
Yeah,
that?
yeah, so all we did, see, look what we got here. We just traded this cosine x for a z and that cosine x for a z
No, for what you just wrote.
up there.
Yes.
All I did was I thought of these because it's less cluttered. I thought of these cosine x's and I just made a substitution and said let cosine x equal z. So it's easier to see that this is just quadratic, right? All we're doing is factoring a quadratic expression. So we went from here down to there, and then we went from there over to there where we factored it. Okay, just like algebra 2 factoring. And then we said, okay, well these really aren't z's. Z is equal to cosine x, so let's write that in terms of cosine x. Did we have to take that detour? No, we didn't. We could have just probably gone straight from there to there, but it just looks cluttered when you have a function as being the variable in which the expression is quadratic, right? It's not quadratic in x, it's quadratic in cosine x. You see what I'm saying? Okay. All right, so once we get this factored, then it's all equal to 0, right? Now, just like before, we would say, okay, if we want to, once we get an equation factored, we apply the zero product property, and we just find the zeros of all the factors. So what are our zeros going to be then? Well, we've got the product is 0 when this factor equals 0. Okay, and would you agree that the first factor is going to equal 0 when 2 cosine x equals 1?
Yeah.
Right? So then, let's kind of color code this. So this one is right here. So there's one solution, right? Here's the other solution. Or cosine x equals -1, right? Okay, those are just unit circle issues, aren't they? Right? So we could rewrite this as
Wait, can't you move the 2?
like that. Yep.
Yeah.
So cosine x equals 1/2. So on the unit circle, where is it that the cosine of x equals 1/2? So it's going to be pi over 3. Good. So we know we're going to be right there. That's going to be a point with coordinates 1/2 square root of 3 over 2, and then its mirror image in quadrant 4, right? So that's going to be a point with x coordinate 1/2, y coordinate negative root 3 over 2. And those angles are, this one is pi thirds, and so this one must be 5/3 pi. Right? Okay, so there's two values of x that are critical numbers, because those are the values of x where 2 cosine x equals 1, or cosine x equals 1/2. How about over here? On the unit circle, where does cosine x equal -1? Yeah, right there, right? That's the only place, at pi. So then my critical numbers are those three places. We get pi thirds, pi, and 5 pi over 3. At least now, there are infinite number of places where these things happen, but remember that our domain is restricted. So on our domain, those are the three critical numbers that we get, right? Okay, let me pause there. Does everybody, and ask, does anybody have questions about that stuff right there, that part of the screen?
No, it makes sense to me,
Yeah,
but I
same.
would never think to do this on my own.
Yeah.
Well, okay, but you
Go
will.
outside.
Now, let's kind of look back here and figure out, well, what did we really do? You know, we do the same stuff we always do. This is, I admit, this is a little tougher because it's a trig function, but just think about, we still are just solving an equation, right? We took a derivative, and then we're just going to set the derivative equal to 0 and solve. Okay, but here's the part where, you know, this kind of takes us back to pre-calc trig a little bit, right? So when you're solving a trig equation, when the angles are different, you've got to use a trig identity to make the angles the same, right? So that's what we did. We used this trig identity right here, right? We made this trig. Cosine 2x is 2 cosine squared x minus 1. There's our trig identity, right? And so now we get a trig equation that we can solve. We've got a trig identity that's got cosine x's in it, and that's it, right? And so we factored it. We factor this trig identity. We've got the 2 out front, but we can factor all this stuff in here. It factors into 2 cosine x minus 1 times cosine x plus 1. And if I FOIL those out, it works. 2 cosine x times cosine x is 2 cosine squared x plus 2 cosine x minus 1 cosine x is plus cosine x minus 1, right? It works, okay? And then like we always would do, once we factor an equation, we're just going to set the factors equal to 0 and solve, right? Those are our solutions, right? So we set them equal to 0, and we got, well, okay, when this equals 0, cosine x equals 1/2. Where is that? Got to go to the unit circle, right? Okay. And so that's the extra step here is, after we factor this and solve it, well, remember, these are trig functions, and so we got to go to, you know, check the unit circle to see where are the angles where cosine x equals 1/2. Where are the angles, or the angle in this case, where cosine x equals -1, and that gives us our three critical numbers. There, there, and there. And now we're just back to our table, right? Okay, so let's start building our table.
But we don't have our second.
Okay, so we're gonna need to do the second derivative, aren't we? So let's, is this gonna be to be continued again? See, we need longer classes. Wouldn't 70 minutes be nice?
No.
Oh,
Yeah, it would.
No. But not for 7 periods.
No, but it's only 5 periods if you have a.